Okay, as Jason mentioned earlier, our next speaker is Brucek Khailany from NVIDIA. Brucek currently leads the ASIC VLSI research group at NVIDIA Research. He leads research efforts into innovative design methodologies for rapid chip development, machine learning-assisted and GPU-assisted EDA algorithms, and energy-efficient accelerator architectures for machine learning. During his time at NVIDIA, Brucek has contributed to projects within both research and product groups on topics spanning computer architecture, microarchitecture, and ASIC VLSI design methodology. Previously, Dr. Khailany was a co-founder and a principal architect at Stream Processor, SPI, where he led research and development activities related to programmable processor architecture. So today, Brucek is going to tell us a little bit more about how we use machine learning in EDA at NVIDIA and how we use that for designing more efficient hardware.
Yeah, I decided to try to get as many buzzwords as possible into my title, and since the Turing Award is on machine learning, I decided to put that in twice. So, so I'll just talk about some of the research that we've been doing in our group. So I'll give some motivation that's similar to many of the other talks. I'll talk about the high productivity Agile design flows that we've been using for building chips kind of entirely in C++. It's a good follow-on to the talk that Jason just gave. And specifically, the research test chips we've built using this flow, which are machine learning accelerators. And then talk about some of the new work we've been doing on applying machine learning and GPUs to EDA. Okay, so I don't think I need to belabor this point too much, but it's just a different view of what others have talked about. Basically, Moore's law is dying or is dead, depending on your perspective. Sometime around 15 years ago, Dennard scaling ended, at which point we could no longer keep increasing chip capability at fixed power and cost. And now, as Moore's law is ending, we're losing the ability to increase capabilities at fixed cost. However, if I project into the future, customer demand is still going up. People still want more computing, so we need to solve this problem. And so the way people are doing this is obviously with acceleration. That's something that NVIDIA has been doing for a long time. But it's getting challenging because if you look at the number of accelerators that go into our SoCs, for example, this is one that goes into autonomous machines such as self-driving cars. It's our Xavier SoC. There's a half dozen or so accelerators. I'm sure SoC diagram from a mobile phone would be similar. We're talking about thousands of engineering years now, and it's growing, and that's very difficult. It makes it hard to address customer needs, even for a big company. So, what does this look like from a commercial perspective? I mean, it takes something like 3 to 5 years to go from this is a good idea, we should put this into a chip, to actually getting a new accelerator or a new feature into a product. And really, we were talking about this at lunch. The thing that dominates in this design cycle is actually the third implement box, if you just talk about the RTL design and verification. The team size for doing RTL design and verification kind of dwarfs the other efforts like figuring out what to build, the architecture efforts, and even to some degree the back-end design type of features. And so that really kind of prohibits which features or which accelerator blocks make it into our SoCs. And we've been working on flows related to this, as have people in academia. And we've been targeting this goal of can we reduce that RTL design and verification cost by approximately 10x. If we could do that, the way it would sort of benefit us and the market in general is allow us to kind of overlap these architecture and implementation phases to get to market faster and also add more features into our products. So how have we been trying to do this? I'm going to talk about 3 things. The first is trying to raise the level of abstraction that we're using for our hardware design. So instead of using manual RTL, let's use high-level languages. We've been using C++. Use tools, so we've been using high-level synthesis, although in a different way than the way Jason just described. And then the other key piece, which is sort of the part that we've been most actively working on as opposed to using third-party tools, is developing libraries and generators to promote reuse in the design flow. We've also been working on Agile VLSI design, and the way we think about Agile is we want small teams designing chips or designing units, and they should be jointly working on architecture, implementation, VLSI together, We should have many iterations through the full flow, like maybe, let's say, daily iterations for the 2 months. Well, the project that we've been doing are about 6 months long, so maybe halfway through the project, we just want to start doing daily iterations all the way from C++ to layout. That gives us dozens of opportunities to fix tool issues, constraints, et cetera. And then from the software community, we can just kind of borrow these things that are known in Agile, which continuous integration, automated tool flows, project management. And as I mentioned, we have this kind of goal that we set that seemed crazy at the time when we started the project, which is, can we just generate a chip in 24 hours from our high-level description in C++? And then the last thing I'm going to talk about briefly is, okay, so this is pretty good. With a small team, I could probably build a small chip roughly on what I can put on a shuttle or a 4 square millimeter test chip. How do we scale up to something that's reticle size or even larger than reticle? It would be hard to do that if we just build much larger chips with a small team. So we've been also exploring building small chiplets and networking them together on a package with highly efficient intra-package interfaces. I'll talk a little bit about that too. Okay, so let me start with the first one, which is raising the level of hardware design abstraction. So the approach that we've been pursuing, we're calling object-oriented HLS-based design. So we're using a high-level synthesis tool as our compiler. But rather than trying to, let's say, directly compile application code to gates, or to RTL, I should say, we're essentially just trying to raise the level of abstraction that hardware experts or hardware designers code in, similar to Chisel and other efforts have been trying that. And then to make their lives more productive, we are trying to develop a highly reusable, high quality of result implementation of many commonly used components in HLS-compatible C++ code. So the approach that we've developed for this we're calling MatchLib, which stands for Modular Approach to Circuits and Hardware Library. We have also open sourced it, so you can go to this GitHub page if you're interested. The idea is like as Mark was talking about, all the things that are sort of commodity, like nobody is like innovating really in building, let's say, an AXI interconnect fabric. So let's just open source those things and make them reusable. We also have like NOC routers, we have arbiters, crossbars, all those kinds of, all the plumbing essentially that you need to build a chip is basically available as C++ code that you can synthesize with third-party HLS tools. We're actually working with Siemens Mentor on the HLS tool support. We have some empirical evidence based on our projects that doing this gets us about a 10x productivity gain compared to manual RTL coding, which is great. But the key thing is once you have coded your design sort of fully in C++ and linked it with this MatchLib library, which is kind of shown in this upper part of the box, like basically we want to just code our architectural models in C++ and then simulate them in System C for doing logic verification and performance verification. Everything from there down, the intention is for it to be pretty much push button. This is kind of where the Agile flows come into play. So if you're interested in this, there's a DAC paper in 2018 that we wrote that kind of explains this whole flow. But the things that we've noted is we can get about a 50x speed up compared to sort of running with a traditional RTL simulator. The performance models are actually quite accurate using the MatchLib components that we've developed. We're seeing like error rates that are in the range of like 3%. That's even given the fact that all of our modules in C++ land are not pipelined. Everything kind of magically happens in a single cycle. And then we take a module and give that to the HLS tool, and it does the hardware pipelining. Most of the error is actually just due to those pipeline startup and shutdown time things. Libraries improve productivity, and we essentially use standard verification approaches, like everything that we use in digital design with constrained random generators, checkers, line expression coverage, functional coverage, assertion, et cetera. We do all that stuff is basically the same. We're just doing it all at the C++ level instead of the RTL level. Right, so the other thing that we've done is said, okay, let's say that problem is solved. Well, if it took me, if I was able to basically iterate on my C model for my design, but fix bugs sort of every few hours or every day, and then it took me a week to push through the tools, it wouldn't be a very agile flow. So how do we get it so that we can essentially, kind of the goal we had in mind is that we sort of fix bugs and then run all the way through the layout flow and then be able to look at the results the next day. So there are really kind of only two things we needed to do to make this happen. Of course, we're at NVIDIA, we could leverage a large team that basically builds a very robust methodology using off-the-shelf CAD tools. But I mean, it's not that dissimilar from what you could get from, let's say, a Synopsys reference flow or something. The two ideas to make this happen is the thing that Andrew talked about, which I think you called it extreme partitioning. So instead of taking like a full 2 square millimeter piece of logic and pushing that through the place and route tools, which might actually take a week, we split everything into really small partitions that are on the order of 0.1 or 0.2 square millimeters, so maybe 150K gates, 150K instances. And so it's just basically simply a divide and conquer approach. If you have enough tool licenses, you can basically push all of your partitions through the tool in about 10 or 12 hours. The good thing about this is in the March to tape out phase for the project, I kind of get like sick, let's say if you're working on that for like 2 months, you get like 60 chances to fix all of your timing constraints and your tool knobs, as opposed to, if I'm basically spending a week or 2 weeks through the tools, I only get like 5 chances or something. So that's kind of the advantage there. The other thing, which I won't go into too much detail, but if you're interested, you could go read this paper that was actually just best paper at Async 2019. The other idea we had was, okay, if I'm building these large chips and I need to basically sign off on synchronous timing closure on all of my interfaces between all my partitions, I essentially have like, a million flip-flops that all need like a balanced clock, and you have to basically do synchronous timing. That would be, that's quite difficult, and also just running through the timing closure tools would be really hard. So let's just like put small little clock generators in each of these tiny partitions, and then have correct by construction asynchronous interfaces between these partitions. You're going to have some overhead because you now have clock domain crossings everywhere, but if you're targeting high productivity, it's possible you can make it work. And the overheads are manageable. Okay, so so that was the flow that we developed, is really kind of those 3 things were the main innovations. And using this process with a team that was on the order of 5 to 10 people in research, we were able to tape out 3 chips in a year. The first chip we taped out in mid-2017. It was really kind of a vehicle for developing this methodology. It was a machine learning accelerator, but the main reason for the tape out was really kind of to develop those 3 things. Most of the work was probably building up the matchlib library. We took that design and showed that with basically 5 engineering months and basically someone doing back-end design services, we could port this to a totally different foundry. So that was a cool result. And then like the next one, which I'll spend a few slides to talk more about, is we then said, okay, we've showed this is possible, but if I'm trying to convince product groups to leverage this, they're not going to really believe the results until you show that you could build something without a performance area or power degradation compared to manual flow. So the third chip was basically to say, could we build something that's essentially a state-of-the-art deep learning inference accelerator for convolutional neural nets, and have it be, and show this productivity advantage, but basically be pretty much on par with an accelerator similar to like the NVDLA open source accelerator, which Dave Patterson talked about. And so I'm happy to report the answer is yes. So I'll talk a little bit about that. So we actually just published this 2 weeks ago, I guess, at VLSI. So I guess, and it's also going to appear at Hot Chips. So the project, as I mentioned, the goal was to say, could we achieve over 100 teraops of inference performance? This is 8-bit integer, and get about 10 teraops per watt, which is pretty much state of the art, and demonstrate it's possible with a very small team in a high productivity flow. So I mentioned, so we used all the pieces I talked about. On top of that, we also basically taped each little chiplet, which is about 6 square millimeters. It's packaged onto a 6x6 MCM, and interconnected together in a network on package, network on chip hybrid network. So the architecture is basically each chiplet has 16 processing elements that just do dot products, essentially. There's distributed weight storage across all the processing elements. There's a chisel-based RISC-V controller that basically runs the runtime that is integrated into basically as an IP block. There's a network on chip that was fully built using MATLAB. And then there's a network on package router as well, which is also using MATLAB, and a GPIO interface that we built as well using that library. So each PE has distributed weight storage, input and activation buffers, vector max for doing dot products, as well as post-processing functions that are typically found in convolutional neural nets. If I dive a bit more into the architecture, you can see a blow up of the PE here on the right. So you can think of the way the chip works is you kind of run one layer at a time, distributed across this huge system. So basically the weights are distributed across many small memories across all of the PEs, and then basically activations sit in the aggregated global PE storage across the MCM. Activations are streamed through the input buffer, and then results are partially accumulated in the accumulation buffer, and we further do some accumulation across the PEs themselves. The main point I actually wanted to make here, since this is actually more of a talk about methodology, is how we implemented this. So if you dive into this processing element, you can see there's a router at the top, router interfaces, these distributed buffers, input buffers, vector MAC units, accumulation buffers, et cetera. This slide shows how all those pieces are implemented. So you can kind of see how, starting out, these green boxes are the pieces where we just use the open source MATLAB, with the appropriate template arguments, essentially, and just instantiated them. So you can see like there's a lot of FIFOs, memories with arbitration structures built in, as well as a cut-through router implementation. That's one of the specializations that we have in the library. And then those are instantiated in a few different ways. So the overall PE is actually 4 System C submodules. And then each System C submodule has a number of C++ classes that are instantiated inside of it. So for example, over here we have a data path class that implements like the vector MAC dot products, the input activation buffer class that implements the streaming of the activations and so forth. So I guess the takeaway point is that we were able to achieve a lot of reuse, which was the original goal, modularity, and use hierarchical design to make this very productive. Okay, so then to scale up, as I mentioned, we have these basically energy efficient intra-package links and a hybrid network on chip, network on package. And this was, it's sort of something we got for free because we had a very efficient intra-package link from a previous circuits group project. But this could work with sort of any arbitrary approach. If you had access to like interposers or other sort of 2.5D integration things, or even if you had low speed. The cool thing is if you're in a research setting, be it academia or industry, the fact that you can build 100 teraops sort of test system with a small team is kind of a cool thing, and I would encourage academics to consider this too. Okay, so here's the benchmarks. I'm probably going to skip over this because I'm running behind on time, but if you're interested, check out the VLSI paper. It achieves basically 128 teraops peak and 10 teraops per watt at its most energy optimal voltage. So I'm going to try to finish by talking about what we're working on now. So, okay, did we declare victory and say, okay, we solved the design productivity problem? Let's just like hand this off to the product group and go retire. No, there's still some challenges. So the first is, and some of these were actually talked about earlier. So one is it's still difficult to predict sort of the VLSI quality of results in terms of routability, timing, area, power from the high-level design. And so that means like so basically if you're making all these architectural changes and trying to decide what to go and do, or it often can still take a while to sort of figure out like what the, you basically just kind of have to try things out. And so that there's still like a lot of churn for that reason. You'd like to be able to kind of just, update your C++ model and say, what's going to happen to run through HLS and like immediately find out what might happen to timing area power. And the second thing is, it's not clear that we found the best physical design implementation because you're still working within, schedule budgets. We'd like to just throw more compute power at this problem and let a tool automatically find the best physical implementation. So those are kind of what I think are interesting opportunities and what we've been working on trying to apply machine learning to. So the first one, this is a combination of work that I'm citing from other people as well as stuff that we've collaborated on internally. So there's a lot of people who are looking at using machine learning or deep learning to do predictors for VLSI, and I think this is a pretty promising research direction. So you can do things like predicting whether you're going to have DRC violations, power dissipation, what your power dissipation is going to be, testability, et cetera. And this is, I think this will be sort of a fruitful area of research moving forward. And then the other area, as I mentioned, is can we use either machine learning tools or GPUs to do this physical design space exploration automatically? So there's been a number of publications, such as from Luca's group, on using ML models to predict QR effects of tool knobs to help with automatic design space exploration. And some work that we just collaborated with UT Austin, which just got best paper at DAC a few weeks ago, the idea was basically using GPUs and deep learning frameworks to parallelize VLSI placement. So the idea, most of the code is actually written in PyTorch. The idea is that it turns out the stochastic gradient descent you need to do for minimizing wire length in global placement is very similar to the stochastic gradient descent you need to do for basically optimizing network weights in a machine learning, a trained machine learning model. And so you can actually just use like all these libraries that are out there to get this stuff running really fast on a GPU. And so using this approach, we were able to show that you could get about a 30x speed up compared to the best academic multi-threaded CPU implementation on this problem. So I think this is also a fruitful area and encourage people that are interested to go down this path. So to summarize, I think the design effort, we can basically address this design complexity problem by raising design abstraction levels, embracing Agile and open source design. And I think I'm really excited about sort of this idea of researching automated physical design space exploration. Wanted to acknowledge all my collaborators at NVIDIA, Harvard, who we worked with on the MatchLib stuff, as well as former NVIDIA interns and postdocs, and DARPA, who helped with some of the funding. Thanks. Right.
Is this enough to start convincing product teams at your company, or is there something else that's methodologically oriented that's still missing? Repeat the question.
Yeah, so the question is, we have a compelling research result in showing that we can, with a small team, tape out this the RC18 chip. Is that enough to convince the product groups that these flows are worth adopting? So let me try to answer that two ways. So first, I should say that many ASIC design houses are already using high-level synthesis for parts of their chips. I think the most common places it's used is often in like image processing, but there's other areas like I've heard that a lot of companies, for example, doing signal processing in other areas as well. Generally, those flows tend to be kind of take a standalone function for implementing some signal processing kernel, map it to RTL, and then sort of surround that with a bunch of like sort of manual RTL scaffolding. so people who have been using that, I don't think need much convincing because, so there is a comfort level there. The question is, could you, so part of the question is like, okay, would you use this to like build a full chip using say System C as we demonstrated? There's still some challenges. So probably, so design verification was mentioned as one. So there's both the issue that although the vendors are working on it, there's still not the C++ to RTL formal equivalent of what we have with RTL to gates. The second issue is actually maybe a little bit even trickier, is that even if you did have that formal C++ to RTL equivalence, I can't necessarily do all of my verification at C++ and not sort of repeat the verification at the RTL level. And the reason is that the timing models are slightly different between the C++ and the RTL. And so you could have a bug in your source code that just wasn't exposed because either it was impossible or hard to generate the case that would have led to the HLS tool exposing the bug after it does hardware pipelining or hardware scheduling. So I think those are still open questions that need to be solved, and I know some people are working on them. So that's probably the way I would answer, yeah. I think on QOR, people are starting to be pretty much convinced. That was an argument like 5 years ago, is like the QOR is worse. I think we've now kind of, I think people have shown that it's like the QOR is pretty good, yeah.
Following up on Abhijit's question, so, but to which extent the problem is the readability of the synthesizable RTL?
I mean, it's definitely,
The fact that
yeah.
well, if I do the physical design, I'm going to fix it.
Yeah, so there's a question about the readability of the synthesized RTL, which is, I would say, a common issue among all of the all the people that are exploring higher level languages, not just HLS. So there's two aspects to this. I think one is the understandability of the downstream tools. Like if I have to like debug some timing path that comes out of my place and route tool, like how do I trace that back to some C++ change? So that's a concern. I mean, the thing you have working for you is that usually the people that are doing like HLS are so far ahead of everyone else that they can kind of like, you know, they're usually not they're not the long pole in trying to get the chip out, you know, and so like maybe that isn't much of an issue. So the other side of the readability aspect is like, what if you find a last-minute functional verification bug and you need to do an ECO? So both of those are not solved problems, but I think they're balanced by the fact that, again, you're so much more productive. There's probably fewer bugs introduced that you're kind of not the long pole in the projects.
Someone's related. You have a chip where you use both HLS and Chisel. Any subtle points that you can share about those experiences? How did it feel?
So one of your ex-students has actually a nice slide set that he could probably be happy to share with you. I think there's pros and cons. So we didn't actually do a lot with Chisel because we're pretty much used a rocket chip, open source rocket chip, and made some small mods, in fairness. So that wouldn't be the greatest comparison, but we do have two people in our group who've used both tools, and so they've kind of had a comparison. I mean, this is really, so first of all, HLS is a tool if you want to give control over hardware scheduling and pipelining to a tool, and you don't want to basically keep it as a designer. So I would never build a processor core using it, for example. But so yeah, I mean, if you want precise control, it's not the right solution. And then there's a whole bunch of things that are related to like maturity. One of the reasons I think HLS is I don't think NVIDIA is going to be uncommon here, but one of the reasons that the HLS is nice is that all of our architecture simulators are built in C++. So like if our goal is essentially to have our synthesizable model very close to the architectural model, that's a big advantage.
So you mentioned this in response to this question. When I was talking to somebody about what you should comment was, or design productivity meetings. He said, look, we spent all our time in design doing validation. So we actually should design to make validation easier, because that's where you spend all your time. And like constructing an RTL, that's not so hard. Validating is hard. And that gets to the question about the debuggability of the output, because if you could just debug at C, perfect, because you got out stuff. But if you have to debug the generated RTL, did you find yourself spending much time at that level?
Right. Okay. So the question, yeah. So just repeat the question. Since verification is the hard part, do you find that if you like introduce a bug that wasn't exposed in system C, that it kind of makes it harder to find that bug? So I guess the empirical evidence is, and Sophia may want to chime in here because she did some of it, but I think it wasn't actually hard. Like in some ways it was actually easier because the code is like more readable by more members of the team. So there were a lot of cases where like so I guess so the hard part was sometimes we would like put something on the emulation, on our FPGA emulation system or run through RTL and it would fail and it would be hard to repro in C++, but we eventually were able to do that, usually because it just meant we didn't run enough cycles with like random stalling or something in the C++ model. And so once you could repro it, it was like way easier to find it and fix it. So yeah, I mean, I guess that's, so I don't, 6 of one, half does the other, I don't know.
If you find it in the source, it's easier, for sure.
For sure, yeah. I mean, right. It's actually like hard to, we don't have like a quantitative measure of exactly why it's more productive from a design and verification perspective. Like there's fewer lines of code, there's more reuse, it's easier to find and fix bugs. These are all kind of hand-wavy arguments, but they seem to hold when we look at the empirical evidence. All right, thanks.